Okay. Previous week we have discussed exponential Fourier series representation of a discrete time signal. Okay, and we see how to draw the phase plot and magnitude plot. It is not much difficult. I didn't send you the video, no. I will send it through mail today or tomorrow. Okay. Um, this is for two. Okay. So this is the Fourier series representation. We use Fourier series representation for periodic signal. Okay. Maybe you can remember that. Okay. For the periodic signal, we used Fourier series representation, and we mainly focus on exponential Fourier series representation because it is somewhat easy. There is another Fourier series representation, that is trigonometric Fourier series representation. Okay. So your basically your exam will be focused will be mainly uh, focusing on complex exponential Fourier series representation. Okay. Maybe you can see maybe you can remember that this is the Fourier series complex exponential Fourier series representation for a continuous time signal. Okay. So any signal can be represented as a collection of complex exponential terms. This complex exponential term is considered as a one frequency component or one harmonic. Okay. So this will be the frequency component of kf naught. Okay. So f naught is the fundamental frequency 2 pi by t naught. Okay. Maybe you can remember we have done this. This is the other one. Discrete is a continuous time. I don't know. It is maybe you can remember the equations. Okay. I will write. Okay. I think maybe you can remember that we see the discrete time complex. Complex exponential Fourier series representation for discrete time signals. Okay, we have two identities. Maybe you can remember that. Okay, so any discrete time signal can be represented as a sum of complex exponential terms e to the power jk omega naught n. Okay, so this complex exponential term is considered to have one frequency component. Okay, so the frequency component will be k omega naught. Okay, so this k will be integer value. Actually k is from 0 to n naught minus 1. Okay, So these are the frequency component which the signal has. Okay, so actually we can't say that any signal we need to, there is a condition, Dirichlet condition. The Dirichlet condition should be satisfied to represent a signal as a Fourier series representation. Okay, so maybe almost all the signals can be represented as a collection of exponential terms. Okay, so we are not much bothering about that conditions. Okay, okay, and this k is from 0 to n naught minus 1. Okay, and this ck is referred as the Fourier series coefficient. This is referred as Fourier series coefficients, and these coefficients can be evaluated using the identity 1 over n naught. So here n from 0 to n naught minus 1, our signal xn sequence, our signal law sequence xn e to the power minus jk omega naught n. Okay, so using this identity, you can estimate this Fourier series coefficient. Okay, so these are the two identities we use to represent a signal as a discrete time signal as a collection of exponential terms. Okay, and this n naught is the fundamental period, and it is equal to uh, the omega naught is equal to 2 pi by n naught. Okay, so these are the identities we used. Okay, maybe you can remember this. And also we have discussed that this ck will be a uh, will be a complex number, like this. Okay, it will be a complex number. So there is a magnitude as well as there is a phase related this complex number. Okay, so if you plot the magnitude, with respect to k, this is referred as magnitude plot. And if you plot the phase of ck, okay, with respect to k, this is referred as phase plot. Okay, so last time we have done one example, and see how to represent the signal as a Fourier series representation, and then how to plot this complex exponential term. Okay, and I think I have asked you to do one question in the in our reference book, the example actually. Okay, this is for continuous time. Okay, we are not bothering about continuous time signal. I show you one example. No, I can't remember actually. Where is that? Yeah, this is the synthesis. These are the equation. Okay, analysis of discrete time periodic signal. Okay, and this one. No? Okay, I asked to represent this one as a Fourier series representation. Okay, so there are general value L and N. Okay, L and N. I think you can understand what is the period of this signal. Can anyone tell what is the period of this signal? I think you have. Can you remember that I asked you to represent this signal as a complex exponential terms? Actually, answers are given. Okay, so I asked you to try this question, this example. Okay, did you try this? Do you able to do this? Are you able to do this by yourself, or should I do this? I hope it will not much difficult, okay? Because you can see that it is a sequence, but it is a general sequence, okay? So you can see that there are some terms from 0 to L minus 1, okay? From 0 to L minus 1. This term is L minus 1, okay? Because this is L, no? So this will be L minus 1, okay? So there are 0 to L minus 1, okay? 0 to L minus 1. So there are uh, up to L, up to L, there are the values will be A, okay? Then the values will be 0. So you can see that this is N, okay? So this will be N plus 1. This will be N plus 1, okay? So you can see that this one is repeating here, okay? This, 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 what is called? This point, this sample is repeating here. This sample is repeating here at N plus 1. So what is the period? So you need to consider, you need to count from here to here, no? So it will be 1, 2 like this. So up to this, it will be N, because this sample is N plus 1. So your period will be N, okay? Your period will be N, okay? So, so using that identities, you can easily represent this, okay? So will you able to get these answers? Will you able to get these answers? And maybe I think I forgot to tell you that there's another one thing. And if you get the magnitude of the uh, of the uh, the magnitude of the magnitude square magnitude of the signal, it is the power of that signal, okay? It is the power of that signal, okay? So if you square magnitude, square of the magnitude, okay? So if you plot the square magnitude, for example, we have plot ck magnitude, okay? So it is the magnitude plot, and if you get the square of the magnitude, and if you plot with respect to k, this is we called power spectrum, okay? This is we called power spectrum, okay? Power spectrum plot, okay? This is a magnitude plot, this is a power spectrum plot, okay? So actually this, if you scale this, it is the signal quantity power, okay? So you know that e to the power j omega naught, for example, c e to the power j omega naught, you can write as c cos theta plus j sin theta, cj sin theta, okay? So what is the energy of this signal? It will be amplitude square divided by a, divided by 2, and this signal power will be again amplitude square divided by 2, okay? So the total signal power will be c square. C is the magnitude, so ck square is the power of the e to the minus e to the power jk omega naught t, ck jk omega naught t, okay? So it will be the power of this term, okay? Did you get it? මොනවාරි තේරෙන්නේ නැත්නම් අහන්න, මේ ඇත්තට අමාරු නැගින්න මම ටක් ගාලා කියන්නේ. හරි. ඔකට දන්නවනේ සයිනසෝඩියල් සිග්නල් එක පවර් එක ඇම්ප්ලිටියුඩ් එකේ වර්ගය බෙදීම දෙක. එතකොට මෙතන there are two sinusoidal terms, okay? So you need to add them together. So your power will be c square, okay? So this term power will be c square, okay? Okay. So we normally refer it as a power density spectrum, okay? Sorry, density spectrum. Power density spectrum plot. If you plot this, and this is referred as power density spectrum, okay? Because we see the spectrum. I think you know what is the spectrum. Spectrum is the frequency domain signal. the time domain signal is normally referred as waveform. Frequency domain signal is normally referred as spectrum. Okay, so this will be the power spectrum, power density spectrum. Okay, so do you able to get this answer? Uh, were you able to get this answer? Should I do this? Can you verify? Okay, anyway, just try to do this by yourself. Okay, so this is not much difficult. Uh, mm, okay, this is not much difficult actually. Okay, the ck is like this. You can represent the ck like this. Okay, so if I just give you a hint. Okay, I will quickly give you a hint. Okay, so you know that this is our signal. Okay, this is our signal. Let's send. Okay, and we have A's from 0 to L minus 1, 0 to L, no? 0 to L, 0 to L minus 1, no? 0 to L minus 1, because this is L, no? So we have A's from 0 to L minus 1, okay? From 0 to L minus 1, this is L minus 1 and this is L, okay? Then this is N, and the sample is repeating that again, N plus 1, okay? So if you count here from here, 1, 2, 3 like this, so here, when it come to here, it will be N, okay? It will be N. So the period is N of this signal, okay? Now you need to represent the Fourier series representation, okay? So that signal can be represented as the collection of sinusoidal signal, complex exponential term signal with the weightage jk omega naught n. Okay, so this k will be from 0 to n n minus 1, because n is the period, so it will be n minus 1. Okay, and ck can be evaluated. Ck can be evaluated as sorry, 1 over n naught is there. Okay, I think I forgot to write it here. Okay, I missed maybe. Okay, yeah, I have right, no? Okay, so this will be 1 over n naught sigma, our signal xn, e to the power minus jk omega naught n, here n from 0 to n minus 1. Okay, so you have to evaluate the ck actually here. Okay, ck, you need to evaluate the ck first. Okay, so if you want to evaluate the c naught, you can easily evaluate it. So that is k is equal to 1. Okay, k is equal to 1. Then c naught will be 1 over n naught is n here, sigma xn e to the power minus jk omega naught n. K is 0, no? Okay, k is 0. So this term will be 1. Okay, so this will be from n from 0 to n minus 1. Okay, so you have c naught here, 1 over n here. Okay, then you will have x0 plus x1 plus like this up to x L minus 1. Okay, then pass xl like this up to x n minus 1. Okay, so you see that up to xl1 the values are a. Okay, these are zeros. Okay, so there are there are so this is L minus 1, but this is starting from 0. Okay, so there are L terms here. There are L terms here. So if you add all these L terms, it will be AL. AL divided by N. So this will be the C naught. Okay. Okay. So C naught is AL divided by N. Okay. When the K is 0, C naught will be AL divided by N. But for others, but for others, the this term will have some complex terms also. Okay, so we will try to get general value here. Okay, so that is C naught. Okay, so let's say that when K is 1 2 like this. Okay, so we will refer this as K, then CK 1 over N naught sigma. Here N from 0 to N minus 1 xn e to the power minus jk omega naught n. Okay, minus jk omega naught n. Okay, so now you have to add, you need to uh, evaluate this term. Okay, you need to evaluate this term. Okay, so if you consider this term, you can see that this is a power series. This is the power series. ගුණෝත්තර ශ්‍රේණියක් කියන්නේ. Okay, so for a power series there is an expression for, so here the terms, actually you no need to add 0 to, so if I if I uh, if I expand this, okay, so you will have like this. Okay, 1 over n naught, 1 over n naught. So here n is 0, the value will be a. N also 0, so it will be 1, so you will have 1 here, plus again x1, the value will be a. Okay, then e to the power jk omega naught n is 1, so you will have e jk omega naught n is 1, plus now n is 2, so x2, so it will also will be a, e to the power minus jk omega naught n is 2 now. Okay, so it will be 2 omega naught. Okay, plus when the n is 3, n3 x3 value, so it will also will be a, e to the power minus jk 3 omega naught. Okay, likewise up to L minus 1, up to L minus 1, the value will be a. Okay, now up to n is L minus 1. Okay, up to n is L minus 1, a to the power a e to the power minus jk omega naught. Now n is L minus 1. Okay, so you can see that this is a power series, and what is the value in omega? Value n e to the power minus jk omega naught. Okay, so this is the ගුණිතය නේ. මෙයා මේකෙන් වැඩි වෙලා මේකේනෝ, ඊළඟට මේක ආපහු මේකෙන් වැඩි වෙලා මේකේනෝ, this one multiplied by this one and you get this one. Okay, so this is a power series. Power series. गुणोत्तर श्रेणी. अरे गुणोत्तर श्रेणी के लिए गुणोत्तर श्रेणी. Okay. So there is a common it is called, there is a common expression for n terms addition of a power series. Okay, so you can find that express and you can apply this here. So otherwise, actually I can't remember that. I am normally using the Euler, what is called now Euler formula, what is Taylor series. Okay, so Taylor series are also used to solve these power series. Okay, Taylor series. Okay, so if you are somewhat familiar with Taylor series, maybe it may be easy. For example, I think Taylor series also represent the same thing. Okay, yeah, Normally I'm using this one, I think this one. Okay, so you can see that this is up to infinity. Okay, so the Taylor series are used. Okay, the Maclaurin expansion, this is under Taylor series. There are many Taylor series expansion. Okay, so this is for so normally Taylor series we use for infinite uh, infinite series. Okay, infinite series. Okay, and so according to this one, if you consider this first Maclaurin expansion, okay, so it is somewhat like this. Okay, so if you have 1 plus x plus x square plus x third, so this is up to infinity. So you can compare this as 1 over 1 minus x is correct, no? 1 over 1 minus x. Okay, so you can use this uh, one to find the value of this one. Okay, for example, so if you consider this one, 1, so this is okay. Okay, and if I multiply this, if I multiply this same value, okay, if I, so let's say that this is 1, okay, and if I multiplied 1 from, okay, so this value is L minus 1, L minus 1. Okay, so if I multiply this by uh, XL, okay, I multiplied by this XL. Okay, so I have, again I have the series XL plus XL1 plus XL plus 2 plus XL plus 3, likewise again up to infinity. So this will be XL 1 minus X. This is the second. So what happens if I reduce 1 by 2? If I reduce 1, if I subtract 2 from 1, what happens? Okay, so these terms are, there are some this term. So here, after some time, you will have here plus xl minus 1 plus xl plus xl plus 1, so on up to infinity. Okay, so if I subtract uh, 2 from 1, what happened? So from XL, these terms will be reduced. No, XL terms gone, L1, L1 terms gone, L2, 2 gone, up to infinity, all terms are cancelled. Okay, then I will have up to L minus 1. Okay, so I will have 1 plus x plus x2 plus x3 plus so on up to xl minus 1. Okay, so I subtract 1, that means 1 over 1 minus x minus xl over 1 minus x. So I will have 1 minus xl, sorry, this is xl. Okay, xl divided by 1 minus x. Okay, so this is the terms, this is the addition of the power series up to L minus 1. Okay, so here also I have up to L minus 1. Okay, if I get this A out, okay, if I get this A out, I have ck ck 1 over n, and if I get out a over n naught, I have 1 plus e to the power jk omega naught plus e to the power minus, okay, minus jk omega naught 2 plus e to the power minus jk omega naught 3, likewise up to e to the power minus jk omega naught L minus 1. Okay, so this one and this one identity. Okay, so here x, actually here x is equal to e to the power minus jk omega naught, this term, no, x is equal to this term. Okay, so I can write this ck as a over n 1 minus e to the power minus jk omega naught divided by 1 minus e. So sorry, this one is L, no? E to the power minus jk omega naught L divided by 1 minus e to the power j minus jk omega naught. Okay, so I can write like this. Okay, I can write like this. Okay, so I think this one. Okay, so already this one we have gotten, no? We have it because omega is equal to 2.5 divided by n. Omega is equal to 2.5 divided by n. Okay, so here omega naught is equal to 2.5 divided by n. So if you apply instead of this omega 2.5 divided by n, this also 2.5 divided by n. Okay, so this term is here. This term is here. Now you can see that this term is taken out from this one. Okay, so you will have so this will be like this because you can see that this one is multiplied by this one, it will be 1, and this one and this one multiplied, these two will be will be add together, so it will be minus 2j. Okay, so you can see that. Okay, this part is taken out, so here these two will be remain. Okay, so then you have this two addition to subtraction. Here they have used the Euler formula. Okay, they have used the Euler formula for this term. Okay, so if you know the Euler formula, ej theta is equal to cos theta plus j sin theta, and e minus j theta is equal to cos theta minus j sin theta. And if you subtract ej theta from e to the power minus j theta, what happened? Cos theta will cancel out, and this will be added together, so it will be 2j sin theta. Okay, so this result is so you can see that this is ej theta minus e to the power minus j theta terms, no? So it will be a sine terms. So this will also be a sine terms. You can see it. Okay. So likewise, you can find this one easily. Okay. So you can find the ck value easily. Then if you get the square, so actually you need to get them. So this one magnitude is same. Ck magnitude is Al because this is a real value. So this square will be the same. Al divided by n square. Okay. But here if you consider this one, this has a complex terms. Okay. Actually this is in polar form. No, you can see that this is in polar form. So you know that. I think I have explained. Okay. The complex number also we can represent as like this: magnitude of a e to the power j base of a, like this. Okay, so this will be the magnitude. Okay, and these terms will be the complex value. So the same uh, composition is there. Okay, same composition is there, and this, if you remove this one, these terms, this one and this one will be the magnitude. Okay, so it is square. Okay, so I think you can get this. So try to get this. I have done it. Okay, so this is how this result is got. Okay, okay. Now I will give you another homework. I will give you another homework. That is, I will give you like this. Uh, so try to evaluate this these terms. Okay, so if the xn is given as sigma 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 k from minus infinity to plus infinity delta n minus 8k. Okay, not 8k, we will take 2k. Okay, so try to evaluate the complex exponential Fourier series representation for this signal, for this xn. Okay, so do this as a homework and try to plot uh, the magnitude plot, phase plot, and power spectrum. Okay, power spectrum. Okay. So try to do this question. Try to do this as a homework. Okay. So if you have any problem, you can ask. Okay. So very easily you can go. This is not a much difficult things. Okay. Very easily you can find this. Okay. So the same kind of example questions will also get to your exam also. Okay. So try to do this one. If you have any problem, you can ask me. Okay. Okay. So we will try to start the Fourier. So that is okay for the Fourier series representation. Okay, we will see the Fourier transform. Okay, we will see the